Okay, for this question, we have two infinite long wires are parallel to each other as shown below. The current in wire 1, the left one, is pointing in the positive z direction out of the page, and the current in wire 2 is in the negative direction, into the page direction. Both currents have the same magnitude. We are going to find what's the magnetic field caused by both wires at point O. First of all, let's draw the free body diagram at point O. So this is my point O, and I have two wires. This is wire 1, wire 2. Distance between the wire and the point O is L. What's the direction of the magnetic field caused by wire 1? If you use the right hand rule, well, you're gonna see that it's in this direction, and this is 90 degrees. Why is 90 degrees? Because if you draw a circle with radius L, like that, magnetic field is going to be tangent to this circle. So this is 90 degrees. Same thing for wire 2. Use right hand rule. Thumb points into the page, and the other finger is going to point in this direction. So this is our B1. B1 is caused by wire 1. B2 is caused by wire 2. And our B net is just the vector sum of these two arrows. That's right here. So we can see that we can write a simple equation here. B net is equal to B1 y component plus B2 y component. Because the x component, they got cancelled out. B1x is here. B2x is opposite direction, so there's no sum. The sum is 0. And since the current in both wires are the same, so they're going to cause the same magnitude of the magnetic field. So B1 and B2, they're the same. So let's just say this is equal to 2BY. And what is BY? BY is the vertical component. This is BY. And that is 2B sine theta. Now we need to figure out what's the theta, what's the angle here. So this is 90 degrees. B1 is perpendicular to the side L, and we are given in the question that this angle is 60 degrees, so this is also 60. So our theta is 30 degrees. And now we need to figure out what's B. We need to find an expression or formula that tell us what B is. Since this is infinitely long wire, so we're going to use the infinite wire equation, where B is equal to, I'm going to write on the side, U naught I 2 pi A. And A is the distance between the wire itself to whatever the point is. So A, I'm just going to call this the distance from wire to the point. And in our case, it's L. So we can say that B net is equal to 2B sine theta. And B is U naught I 2 pi L sine 30. And sine 30 is just 1/2. 1/2 and 2, they're going to cancel out. So in the end, we are left with 2 U naught I 2 pi L. And that is option B. Okay, question 9. A particle with this much mass, this much charge, has a speed of 30 meters per second at point A and moves with only electric forces acting on it to point B, where its speed is increased to 80 meters per second. Determine the electric potential difference VA minus VB. Okay, so this is a type of conservation of energy question. Where all my delta KE becomes my delta U. So the kinetic energy is transformed into potential energy. The total energy doesn't change. So that's why I put delta. And what is our delta KE? Since we're given velocity, so we can do delta KE. Remember, for KE, the formula is 1/2 times mass times velocity squared. And now we're looking for the delta. We're looking for the difference. So that's 1/2 m v2 squared minus v1 squared. Plugging the numbers we're given. Pay attention that mass is measured in kilograms. And in the question statement, we're given in gram. So we need to do a bit of unit conversion to convert grams into kilograms. So instead of 10 to the power of -6, it's going to be -9. Now we're in kilograms. Velocity is always in meters per second. And V2 is 80. 80 squared minus V1, which is 30 squared. And that gives me 5.5 times 10 to the power of -6 units joule, because we're dealing with energy. And that means this much of kinetic energy becomes potential energy. So I can say that delta U is the same value of delta K. Okay. And in the formula sheet, you will see an equation that looks like this. Delta V is equal to delta U divided by charge. Do we have charge? Yes, we do. And pay attention, it's a negative charge. Coulomb. And that gives me -1.1 times 10 to the power of 3 volts. So the answer is C. Okay, question 11 says that the second segment of wire total length is equal to 6R, including the incoming and outgoing portions of the wire, is formed into the shape shown and carries a current I. What is the magnitude of the resulting magnetic field at point P? So this is a Biot-Savart question where you have a nasty integral to do. First of all, we're going to break this question into two parts. Well, actually 3 parts. We're going to do that step by step. Let's label part 1, part 2, and part 3. Let's say for segment 1, B is 0. Why is B 0? Because let's write down the Biot-Savart equation. B is equal to U naught I over 4 pi times the integral of dl cross r hat over r squared. So we can draw what happens for segment 1. So segment 1 is right here. Point P is here. Current flows in this direction. So our dl, remember that dl, it's in the same direction as our current. So this is dl. dl is the length vector pointing in the same direction as the current. What is r hat? R hat is the unit vector. The magnitude of r hat is 1, so it doesn't matter. But what does matter is the direction of r hat. R hat is pointing from dl to our point. So r hat, let's say r hat is, this is r hat. And since this is a cross product, this is not a simple multiplication, so we need to consider the angle between these two. So dl cross r hat is equal to dl times 1. Like I said, r hat, the unit vector, has a magnitude of 1. And don't forget to multiply by the angle between them. And since this is a cross, we're using sine. And what is the data? What's the angle between dl and r hat? That's 180. Actually, no, that's sine 0, because they are parallel and parallel in the same direction. That's sine 0. So this 0, this is 0. So B for segment 1 is 0. How about for segment 3? Segment 3 is here, the vertical one. Let's draw segment 3. This is P. This is current is flowing upward. So dl is here. And r hat, like I said before, r hat is pointing from dl to our point. So r hat is right here. And let's write down the Biot Savart. U naught I over 4 pi times integral of dl cross r hat over r squared. And you see that the part dl cross r hat is equal to dl times r times 1. That's the magnitude of r hat, the unit vector, times the angle between these two. And in this case, that's going to be 180 degrees. 180 degrees, 0, 0. So this whole part is gone. So segment 3, so B for segment 3 is 0. Now we are left with segment 2, where we have an arc. And let's also draw this. This is our P. And that's not good. This is our piece here. And current flows in this direction. So B is equal to U naught I over 4 pi integral dl cross r hat over r squared. Now, let's draw dl. Where is dl? dl is a very small section on the arc. This is dl. And what is r hat? R hat points from dl to our point. This is r hat. And they are perpendicular. So we got sine 90, which is not 0, which is 1. That's good. So let's break this down. Personally, I'll say I prefer doing this way. I'm going to break this whole equation into small pieces. I'm going to call where dl cross r hat is equal to dl times 1 times sine 90, which is just dl, because sine 90 is 1. And what is dl? dl is a small part on the wire. Although I draw it straight, but it is not straight. It is curved. It follows the curvature of the curved wire. So dl is basically the arc length. So we're gonna, what is arc length? Is R the data. We have it use data. I'm gonna call it d phi. What is R? What is d phi? R is the radius to my point P. And this is also R. What is d phi? D phi is the angle here. This is not the angle between dl and univector R. That's data. And phi is the angle, well, created by the length of dl from the point P. That's d phi. We are integrating over an angle right now. And what is r hat? Sorry, r squared. Well, r squared, what is r first of all? R is the distance from dl to P. So r hat, r squared is just basically br squared, the radius squared. So now we have everything we need for the integral. Let's write down. So b is u naught I over 4 pi. This thing is always outside of the integral because it's a constant. And dl cross r hat right now just becomes r d phi. This is our dl. And r squared is r squared. And also, we're going to need to find out the integral bounds. And we are given 1/4 of the circle. So this is 0 to pi over 2. Remember, a full circle is 2 pi. So half circle is pi. Half it again, 1/4 is pi over 2. And pay attention that we are integrating with respect to data. So only data should be left inside the integral. Everything that's not data, it's a constant, and constant goes outside. And r, since r represents radius, and radius never changes, so r is a constant and goes outside. Integral from 0 to pi over 2 with respect to phi. And that integral is just phi. And we're going to evaluate at 0 and pi over 2. So we just plug in the value of pi over 2 into phi. Times pi over 2. Pi cancel out, and we got u naught I over 8r. What option is this? U naught I over 8r, that's A. Okay, this is a long answer question. The figure shows the top view of a long straight wire and a circular loop, both carrying current I. The loop and the wire are on the same plane. Determine the magnetic field, both magnitude and direction at the center of the loop. That's question A. Direction of the current is also given in the diagram. So let's do A first. Since we have two wires both generating a magnetic field, so our B total or B net is equal to B, I'm gonna call the long wire just wire, plus B ring. It's a circular loop. Well, a circular loop is basically just a ring. Let's do B wire first. And I'm gonna call it a vector because we have magnitude and direction. We need to consider both components. And look at the keywords in the question. This is a long straight wire. What does that mean? That means we can use the formula for infinite wire. And that's a direct copy paste from the formula sheet. And that is why in the notes it said, you can use the formula provided in the formula sheet, but that's only for the straight wire. So that's u naught I over 2 pi a, where a is the distance from the wire to the point, and in this case, it's actually B. What's the direction? Well, use right hand rule. Thumb is pointing in the same direction of the current, pointing to the right, and curve your fingers downward. So it's gonna go into the page. Into the page is cross. And how about B ring? We're gonna derive this ourselves using Biot-Savart. We're gonna draw this again, just for the ring. We have center right there. Let's say DL. I'm gonna write down Biot-Savart equation first. That's like U naught I 4 pi integral dl cross r hat over r squared. We just did a bit of Biot-Savart before. It's pretty similar to the question before. In this case, we're just having a full circle instead of part of a circle, but it's the same idea. So let's say this is my radius. What's the radius? It's actually A. DL is right here. R hat, remember? R hat is from DL to the center. This is R hat in that direction and perpendicular to DL. So we're good. We have a value. It's not sine 0, it's actually sine 90. And sine 90 is 1. This is also our radius A. This is our angle phi. So where DL cross R hat gives me DL. Look, I'm not writing the unit vector. I'm not writing the vector arrow symbol in this case because I'm writing the magnitude of this value times 1. Unit vector R is having, it has a value of 1, and what matters is the direction it forms, times 90. Good news is sine 90 is 1. So this is just DL. What is DL? DL is arc length. Arc length is R d phi, and in this question we define radius to be A, so A d phi. And R squared is basically radius squared, so A squared. So B ring is equal to U naught I over 4 pi times integral of DL cross R hat got simplified into A d phi. And R squared is A squared. The bounds of integral is from 0 to 2 pi because we have a full circle. A full circle is 0 to 2 pi. And like I said before, A is radius. Radius is constant. So constant goes outside of integral. Times, well, the integral is just phi. If you solve this integral, this is integral of nothing, d phi, that gives me phi. And evaluate at 0 and 2 pi. 0 is 0, so 2 pi is 2 pi. So this gives me U naught I. Pi is gone, so 8A. No, actually this is not 8A. It is actually 2 cancel out 4, so we got 2A. And what's the direction? Let's add this vector symbol. So direction, use your right hand rule. Current flows counterclockwise. So your thumb points into the page. Into the page. Okay, so A is done. Let's do B. What is B talking about? If we suddenly cut a long straight wire, what happens to the current in the loop? Okay, so that brings us to Lang's law. So we have this long wire, and we have this circle. We say that we have a magnetic field generating by the long wire, and it's coming out of the page here and into the page here. And this ring itself has a magnetic field into the ring, into the page in the center. Now, if this wire is gone, what happens to the current? Yeah, what happens to the current in the loop? So let's do Lang's law. Well, first, like originally, I'm gonna say that, like originally, I mean, when this wire is still here, like before the long wire is cut, it creates a B field into the page at a point, what's it called? Point, what's the point? At the center. Of the loop. Now it's cut. So our B is decreasing. And according to Lang's law, if B decreases, B induced is going to be in the same direction. And that is into the page. So now we have basically and B induced in the same direction. So our current will have another component. We're gonna have a so B induced into the page direction is gonna cause an I induced in counterclockwise direction. And since the original current is already flowing in the counterclockwise direction, so our conclusion will just be I total is increased. All right, question 17, we have an inductor L, that's 0.4 Henry, a resistor R, that's 500 ohms, and a capacitor C is equal to 5 microfarad. And they are connected in series to a 50 Hertz AC source that produces a peak current of I max, that's 0.25 amps. Determine ABC. Okay, so in question A, we need to find voltage V max. In the formula sheet, you will see an equation like this. Delta V max is equal to I max times impedance. And I max is given. That's 0.25. So we need to find impedance. And impedance is given by this formula. R square, resistance, it's given, that's 500. We need to find XL and XC. XL is equal to angular frequency times L, is equal to 2 pi f times L. So 2 pi times frequency is 50 hertz, and L is 0.4. That gives me this much. The unit is actually ohm. XC is the inverse of angular velocity, angular frequency times C. Okay, so now we can do Z. And that gives me 714.9 ohm. So Vmax is equal to 0.25 times Z. And that is around 178.7 ohm. Question B, phase angle phi. Well, phi is just the angle, so tangent inverse of, this is L over R. We have odd ingredients, just plug in numbers. And pay attention, you can use either degree mode or radian modes. I prefer using degree modes. It's a negative angle. If you want to do radian, you have a value for degree, you want to do a radian. How do you do that? Degree times, a full circle is 360 degrees. And each full circle, that's 2 pi rad. That's how you do unit conversion from degree to radian, and that gives me negative rad. Just in case if your teacher wants both, like both values, but it's not necessary to do both. And since that we see a negative angle, what does that mean? That means our delta Vmax lags, let's say it's lagging behind Imax. We're gonna need this information for C, because C, we're gonna draw the phase diagram. Let me change color. And here you see that our XL is smaller than XC. So that means our delta VL is actually shorter than delta VC. Let's say this is delta VL and delta VC is longer. And we have this is delta VR, we have delta I max. And like I said, since we have a negative phase angle, so Vmax is lagging behind Imax, and everything here spins in this direction. So that means my delta Vmax is somewhere here. And this is my angle phi. Question 18. As shown in the figure, a long wire carries a current I1 is equal to 30 amps. So the top current is 30 amps, and a rectangular loop carrying a current I2 is equal to 20 amps. Take the dimensions to be A is equal to 1 centimeter, and B is equal to 8 centimeters, and L is equal to 30 centimeters. In unit vector notation, what is the net force on the loop due to I1? So we're looking for the force acting on the loop. First of all, I'm going to break this into, let's say, 4 parts. And we're going to calculate a force acting on each side step by step, and then we're going to sum up all the forces. And it says force due to loop, force on the loop due to I1. I1 is right here. So we can use our right-hand rule because the loop is below I1. So the direction of the magnetic field caused by I1 is into the page here. Okay, let's do side 1, the top horizontal part. We use the formula force is equal to IL cross B. And we're gonna label clearly what is what. Since this is I1, I'm gonna call it force 1. What is IL and B? B is caused by the other one, the other current. So I1. So this is B1. And IL, what is I? I is the current flowing in its own wire. So that's I2. And this is a cross product. We're gonna do I L B1 sine theta. Theta, well, I1 is parallel to no, it's not parallel. It's the magnetic field and the wire. Both wires are parallel, but in this case, I2 and B1, because B1 is into the page and I2 is flowing to the right, they are perpendicular. I almost put a 0 there. So this is actually 90, and this is just 1. So that gives me I2L B1. We need to find B1. B1, it's a long wire. So it's a direct copy from the formula sheet. U naught I over 2 pi A. A is the distance between these two currents. And what is I? I is, since we're dealing with B1, so I is I1. That gives me 4 pi times 10 to the power of -7 times 30 over 2 pi. What is A? A is 1 centimeter. That gives me 0.0006 T. Plug in this value into our force. So we have I2. I2 is 20 amps. And L is the length of this section, not the whole loop, but just section where I labeled 1. So that's 30 centimeters. Times the magnetic field caused by Y1. And that gives me around Newton, what's the direction? Well, gonna use your right hand rule. Current flowing to the right, that's your index finger pointing to the right. Magnetic field goes into the page, your middle finger goes into the page, and your thumb points north. So that's positive J direction. We can do side 3 next, because it's basically the same thing as side 1. The only thing is the distance is changed. So let's call it F3 is equal to IL cross B. Again, B is caused by I1, so this is B1. And I is its own current, I2. B1 doesn't change. Well, B1 does change, because the distance is going to change. So here, B1 for side 3 is going to be U naught I over 2 pi, what's the distance, is A plus B. A plus B, so 9 centimeters. Like that. And that gives me a value of this much. So F3 is equal to I2 is the same, 20 amps. Length is the same. Since the distance changed, the magnetic field changed. So force is going to decrease because it's further away from the source. What's the direction? Well, right hand rule. Index finger pointing to the left, following the direction of the current. Magnetic field into the page, that's your middle finger, and see where your thumb is pointing. Negative J. Or you can say put an arrow here, this is going up, this is going down. Side 2 and side 4. Side 2 and side 4, well, we can just say they got cancelled out. If you just do, because we know the value is going to be the same for the force, but the direction is going to cancel out. Look at this. So 4, current is coming down. For 2, current is going up. Let's do 2 first. So force 2 is to the left, and force 4 is going to be pointing to the right. So force 2 and force 4, the net force is 0. So the only sides on this loop that can feel a force is actually the top one and the bottom one. Well, all sides can feel a force, but 2 and 4 in a different direction, so cancel out. So the total F net is equal to F1 plus F3. That's in a positive J direction plus this much in the negative J direction. So basically this minus that. And the final direction is still pointing up. Question 19. A square conducting loop of side A and resistance R passes through a region of space that has uniform magnetic field B into the page. as shown in the figure. Assume that the speed of the loop is constant throughout its motion. What is the magnitude and direction of the current in the loop in ABC questions? Question A, as he enters the magnetic field, okay, so this is a combination of Lenz's law and Faraday's law. Let's figure out the direction of the current first. Let's do this step by step. Step one. When this loop is still outside the magnetic field, so I'm gonna call magnetic flux B original is 0 because it's still outside of the field. Now it's gonna enter. That means our flux is gonna increase. And according to Lenz's law, if the flux is gonna increase, then the B induced is gonna be in the opposite direction as the original B field. And since the original B field is going into the page, then that means our B induced is coming out of the page. And then you can use this to do your right-hand rule. So your I induced is CCW. Okay, Lenz's law tells us the direction. What about the value? That depends on Faraday. Induced EMF is equal to N times d phi b over dt. Well, N is a single loop, so N is 1. And phi b is BA over dt. B is magnetic field. It's uniform, we don't touch it. And A is the area of this loop. It's a square, so side times side. So it's B times A over dt. And that's B times A dt. And what is this thing? This is our velocity, BAV. This is the induced EMF. So current induced is just basically EMF over resistance. There you go. Question B says that when the square is traveling inside the magnetic field, then we can say that it's 0. The induced EMF is 0 because B is constant, meaning d phi b over dt is 0. Nothing changes. And induced EMF is 0, meaning I induced is 0. How about C? When it leaves the magnetic field, well, it's just the opposite of A when it enters the field. Let's do it. So let's say step 1, when the square is still inside this magnetic field, I'm gonna call it B original is constant. And now it's gonna leave this field. So that means B is gonna be original is gonna decrease. And according to why it's gonna decrease? Because area is gonna decrease. And according to Lenz's law, when the field decreases, you're gonna cause an induced field in the same direction. Remember this: when the field increases, like A, the induced field is in the opposite direction, and when the field decreases, the induced field is following the same direction. So be induced in the same direction into the page, and use your right hand rule. Your I induced flows in clockwise direction. And the back EMF, well, it's the same. Let me just call it PAV. We derived this earlier. And I induced is EMF over R. This. Okay, the last question. An insulating sphere shell with inner radius A and outer radius B is uniformly charged with charge density rho. Determine the following stuff. Okay, so this is Gaussian sphere type of question. You need to know two equations. First, the sphere's volume. That is 4/3 pi radius cube, and the sphere's surface area. And that is 4 pi radius squared. Question A, when A is smaller than R is smaller than B. So for A, let's say R is right here. Draw the Gaussian surface. R is between A and B. We know that Gauss's law tells us this. The closed surface integral of E dot dA is equal to Qn over epsilon naught. And E dA is just EA, so E, isolate E, we got Qn over area times epsilon naught. We need area, we also need volume, because this charge depends on volume. You got more volume, you got more charge. You got less volume, you got less charge. Okay. So for A smaller than R, smaller than B, our E is equal to Qn over A. What is A? A is R, is this Gaussian surface with radius R. Label that over epsilon naught. Now we need to do Qn. This is the charge. What's the charge in this region? Because the sphere is hollow inside. Inside here, there's nothing. So we need to remove the charge here. There's no charge anyway. Remove the volume there, because that volume doesn't create any charge. That's where we're gonna use the volume equation. And charge is equal to charge density times volume. Charge density is represented by rho. And well, in this case, it's a volume difference. So we're gonna say V big minus V small. V big is the sphere with radius R, and V small is this hollow region times V big is 4/3 pi times the radius cube difference. r1 cube, r is right here, this radius, the big radius, minus the small radius, which is just a in this case. And that gives me 4/3 pi rho r1 cube minus a cube. And our surface area AR is equal to 4 pi r cube square is the surface area of this sphere. So our E is just equal to Qn is that much, divided by area times epsilon naught. We can cancel out some terms. We can simplify this, and in the end, we are left with rho for B, where R is greater than B. So in this case, R is outside. Let's say R is here. Let's label it R2. This is so ugly. Okay, better. So same thing, E is equal to Qn over A epsilon naught. And epsilon naught, Qn is equal to rho times the volume difference, V big minus V small. And let's look at what is V big, what is V small. V big is this radius, and V small is this radius. So that is 4/3 pi rho times r cube minus b cube. And A is still this big sphere. So that gives me and we are left with rho. This pi is gone, 4 is gone, this, and don't forget the epsilon naught. Okay.